Hi everyone. So I'm going to talk over next section, getting into the next chapter, section 8-2. This is the basics of hypothesis testing. So just keep in mind this is a very conceptual topic here with hypothesis testing. So please just make sure pause videos, rewatch the clips or anything as much as you need to try and help understand these concepts. So far, what we've done with inferential statistics, and what I mean by inferential statistics is, so if we draw conclusions and or make decisions concerning a population based on only sample data, it's just a nice little summary of what inferential statistics is. So far what we've done with that is in confidence intervals in chapter 7, where we can use the confidence intervals to say we are so confident a population parameter is in the interval, and that's all just based on only sample data. So now what we're going to do in chapter 8 is we'll test whether or not a claim about a population or treatment is valid. So kind of ultimately, like, if we're told, say, a medicine works better than other ones, then this is a statistical test that we can use to see if that's actually true or not. Now, all of this for hypothesis testing is based off the rare event rule for inferential statistics, which the way that goes is if under a given assumption, the probability of a particular observed event is exceptionally small, we conclude that the assumption is probably not correct. So again, in essence, if a probability of something is really small, we're not saying the probability is bad, we're saying that whatever our assumption was before must not be correct. So now, in a nutshell, some things that go on with hypothesis testing is we make hypotheses based on a claim of some sort. We decide on possible error levels, so just how much wiggle room we have essentially. We use a sample statistic, so just sample data, to test a claim relative to the error levels. Then we make a conclusion using technical statistical language, which you'll see kind of some general phrasings for those language conclusions here. Then we translate that conclusion into context using non-statistical language. Your book splits this into 8 steps, and somewhere around 7 to 8 steps seems to be pretty common for splitting these up, depending on which text you look at. Again, just expanding on that, so key concepts that we want to try and make sure we understand just by the end of this chapter section is how to identify the null hypothesis and alternative hypothesis from a given claim, and how to express both in symbolic form, and how to calculate the value of the test statistic given a claim and sample data, how to choose a sampling distribution that is relevant, how to identify the p-value or identify the critical values, and then how to state the conclusion about a claim in simple and non-technical terms. There's just some little definitions here to start with. So what we're talking about with the hypothesis in the context of statistics here is a hypothesis is a claim or statement about a property of a population. So just kind of what we're going to test or claim. Then the hypothesis test is a procedure for testing a claim about a property of a population. Again, all about we're going to claim something, then we're going to test it. So the two types of hypotheses you're going to have in hypotheses tests are the null hypothesis, which is denoted by H naught is what this symbol means, or H null. It looks like this little H sub 0, you just commonly hear it referred to as H naught, is a statement that the value of a population parameter, such as a proportion, mean, or standard deviation, is equal to some claimed value. Now, in this book, we're always going to use equal to for the null hypothesis. And big idea with that is we test the null hypothesis directly in the sense that we assume it is true and reach a conclusion to either reject H naught or fail to reject H naught. So key things there, we're always testing the null hypothesis. And then from there, our conclusions can be that we reject that hypothesis or we fail to reject. Notice the word accept is not anywhere in here. It's just fail to reject or reject. And the other hypothesis is the alternative hypothesis, denoted usually by H1 or H sub A is also pretty common. is the statement that the parameter has a value that somehow differs from the null hypothesis. And the symbolic form for the alternative hypotheses can use symbols like less than, greater than, or not equal to. Basically, it's just got to be something different from the null hypothesis, or some form of opposite from the null hypothesis. Now, just a little note here about the claims that you use. If you're conducting a study and want to use a hypothesis test to support your claim, the claim must be worded so that it becomes the alternative hypothesis. So ultimately, this is trying to tell you just be cautious and be mindful with your wording of any claims in hypothesis tests. Because if we want to be able to say that something is supporting a claim, we need to make sure that our claim is the hypothesis that is some form of not equal. Like say I want to claim that some medicine gives greater results than another, then the null hypothesis could be that the results are the same, so they're equal. Then the alternative hypothesis could be that the results are greater, so that form non-equals. And if it worked out where I rejected the null hypothesis, I'd be supporting my claim that these other medicine was better. And this is a little chart here to help kind of identify the first three steps for a hypothesis test. So identify the specific claim or hypothesis to be tested and put it in symbolic form. So this will usually be you're trying to figure out what your H naught is, or your null hypothesis. Then give the symbolic form that must be true when the original claim is false. So some form of like an opposite hypothesis, usually going to be the the alternative hypothesis here. And then step 3, just kind of making sure you've got the null and alternative hypotheses correctly split up. So of the two symbolic expressions obtained so far, just make sure that the alternative hypothesis is the one that does not contain any sort of equality. So it could have the less than, greater than, or not equal to. Then just make sure that the null hypothesis is the one that has some form of equals in the claim, or sorry, in the hypothesis. So an example for that can be based on this context here. Assume that 100 babies are born to 100 couples treated with the XORT method of gender selection, that is the claimed to make girls more likely. So this is some treatment that basically we're testing here, and the claim is that this treatment works better. So we observe 58 girls and 100 babies, then write the hypotheses to test the claim with the XORT method. The proportion of girls is greater than 50% that occurs without any treatment. So this is a case where we're trying to support some claim that the XORT program works better, or XORT method works better. And so in this case, again, we want the null hypothesis to always be some form of equals. And usually when we try and say something is better, we just compare it to a majority or 50%. So that's why we're saying that the proportion should be equal to 50% or 0.5 for the null hypothesis. Just saying that basically there would be a 50-50 chance of having a boy or a girl. So this would be where there could be no change. And the alternative hypothesis would be just that the chances of having a girl are greater than 50%, just saying that the XORT method would work better. So that's why in this case, this one would have to be greater than 0.5. Alright, step 4 is to select the significance level. Now this is, you can kind of think of the significance level as like a threshold when you're doing hypotheses tests. And so for this, it says select the significance level alpha based on the seriousness of a type 1 error. So there are two types of errors with hypotheses tests, type 1 and type 2. And we'll talk a little bit more about what each of those errors are like in a bit here. Make alpha small if the consequences of rejecting a true H0 are severe. The values of 0.05 and 0.01 are very common, especially the 0.05. That's got to be probably the most common one. And so again, just talking a little bit more about that, significance level is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true, or in simpler terms, making the mistake of rejecting the null hypothesis when it is true. So, like, say for this context, say we accidentally reject the null hypothesis that basically there's no change in the with the XOR method, but it was actually true. That'd be a type 1 error. Next step in the A-step process is we're going to find our test statistic and determine which sampling distribution we need to test it with. Now, ultimately, the test statistic is kind of what you get from a sample statistic and then turn it into a z-score, t-score, or chi-square score of some sort. So, like, say for example, you have sample proportion data and you've got all your other requirements satisfied. You can plug everything into this formula here. You get a z-score based on that sample proportion, and now that becomes your test statistic. Same idea with means. You could just use a sample mean, plug it into that formula, you get your test statistic. And then only differences here with means is same as before, where we use z-scores if we know the population standard deviation. And if we don't know the population standard deviation typically, then that's when we use that t distribution. And for testing variances or standard deviations, that's when we use those chi-square values. So again, the test statistic is a value used in making a decision about the null hypothesis and is found by converting the sample statistic to a score, so that z-score, t-score, or chi-square score, with the assumption that the null hypothesis is true. So ultimately, this is what we're going to use to test the null hypothesis. So now step 6 in that process is just finding the value of the test statistic, then find either the p-value or the critical values. So we first transform the relevant sample statistic to a standardized score called the test statistic. So in step 5, we were just deciding what kind of test statistic and distribution we'll need. Step 6, we actually find it. Then we find the p-value or the critical values. Now this p-value, this is a type of probability. Now an example, or talk over this, and then we'll get a bit more into what kind of a probability a p-value is. And so let's again consider the claim that the XORT method of gender selection increases the likelihood of having a baby girl. So our preliminary results from a test of the XORT method of gender selection involved 100 couples who gave birth to 58 girls and 42 boys. So use the given claim and preliminary results to calculate the value of the test statistic. And we're going to use the format of the test statistic given above so that a normal distribution is used approximated by normal distribution. Ultimately, we're just going to get to use the normal distribution for this one, or z-scores. And so now the claim that the XOR method of gender selection increases the likelihood of having a baby girl results in the following null and alternative hypothesis. Same null and alternative hypotheses from before. So we work under the assumption that the null hypothesis is true with that proportion equal to 50% or 0.5. Now the sample proportion of 58 girls and 100 births results in just that p hat being equal to 0.58. So that's what we're going to plug in to find our test statistic. So again, our test statistic is once we actually find that final z-score in this case. So we plug in that 0.58. And we plug in our claimed proportion value in for everything else. Once we would evaluate that, we would find our test statistic comes out to 1.6. And just based on previous chapters, we know that a z-score of 1.6 falls within a usual range because it's within 2 standard deviations on either side. And at first glance, 58 girls and 100 births does not seem to support the claim that the XORT method increases the likelihood of having a girl, more than 50% chance. And so we can do something and then pick up in the next video, but also this is just kind of what happens when you get a test statistic, and then we'll go from there to see if we can use that to find any other conclusions.